Start. Hello everyone, welcome to our project presentation of EEE 416. We are group 2 from B1. Our project is about making a privacy preserving GPS system. Moving on. This is the outline of today's presentation. Moving on. We have interfaced GPS module initially with Arduino Uno for earning a good understanding about the project. After that, we have done the same task using Context M4 microprocessor. PCB layout has been designed and 3D rendering has also been done for the system. Moving on. Background. Global positioning system is a very useful technology in today's world. A very common example is by turning on GPS in our phone. We can get exact location of us and anyone we wanted to. This feature helps to create large company like Uber, but how they use GPS data to locate driver and traveler, then find nearest driver. Besides GPS used in many fields like agriculture, aviation, environment, marine, public safety, and disaster, rail serving, and mapping. Moving on. Now we will discuss about how we can interface with GPS. This is the algorithm of interfacing with GPS. At first, we will read GPS data using GPS module through Universal Synchronous Asynchronous Receiver Transmitter USRT communication protocol. Then this data will be transmitted to STM32 controller. After processing in controller, we will get displayable data which will be shown in display or in virtual terminal. Moving on. We get GPS data in GPGSB format. In this format, the first 9 digits after GPGSB represent UTC time of in hour, minute, second format. Next character represent status of GPS data. A means data is valid, B means navigation received a warning. Next data show latitude and longitude. So after parsing this data, we can show this data in display. This will further discussed in the code section. Moving on to the next presenter.
Hello, my student ID is 71. Here we have implemented the GPS interfacing by using Arduino and STM32 separately. For implementing with Arduino, we need Arduino board, breadboard, GPS module, LCD display, potentiometer, and jumper wires. For STM32 implementation, we need STM32 Cortex M4 microprocessor, GPS module, and LCD display. The main source code is written in C language, but the STM32 controller is unable to read this high-level language. So firstly, we have to convert this high-level C language into machine language or hex file. For generating hex file, we have used Kale new version compiler which receives C file as input and gives us the desired hex file as output. This Kale generated hex file is then given input to STM microcontroller. Now let's move on to source code explanation. I have divided the whole code into various segments and we'll talk about each segment separately. We will need bunch of functions to implement our task. These functions are built into some header files by default. So at first we have added those header files to use those built-in functions. Then there are some data structures which are necessary to use GPS module. So we have declared those data structures and also some user-defined variables for data manipulation. Then the whole system needs to be initialized before start functioning. For this, the system init function is used and also the GPS module is initialized by tm_gps_init function. We know that GPS module receives data from the satellite continuously. So for updating the GPS data time to time, this tm_gps_update function is used and the received location coordinate is stored in result variable. So after the initialization of GPS module, the system will check if any update data is available in GPS. If no data is found within 3 seconds of the initialization, then the virtual terminal will show new received data have not valid GPS signal. If result equal tm_gps_result_new data, this condition is satisfied. That means a new updated data is received by GPS module from satellite. Now this data should be checked whether it is valid or invalid. As we know, the longitude and latitude has a defined and designated range. If the received data value is not in that range, that means it is an invalid data. This validity is checked by this number 6 code segment. If the data validity statement is true, then the virtual terminal will show new received data have valid GPS signal. Now, in the previous code segment, we have checked the validity of the data. Now, it is in this code segment, this data will be displayed, the received data is in GPGGA format. This code segment prints the attributes of GPGGA, such as latitude, longitude, satellite in use, UTC time, and so on. After the execution of this code segment, the virtual terminal will show the data received from satellite. Now moving on to next presenter.
After that, the GPGSV statement is shown and the satellites in use in view are shown. After that, the buffer holds this output. Then a new line is given by dashed lines. Then the GPS waits for a new data, and if no new data is received, then it shows the old data again and again. Now moving on to the demonstration part. At first we can moving on to the demonstration part. At first we can see that the virtual terminal displays at first you can see that the virtual terminal displays no new data has been given. Then using virtual GPS, we have given a specific location as input. After some delay, it receives the valid data, and as the format explained earlier, the following data is displayed. We have also implemented the following data is displayed, and then we have also done this using another location, which is New Market, Dhaka, and then the GPS module receives that coordinate and the data are displayed on the virtual terminal. We have also implemented this using Arduino, but due to shortage of time, we are unable to explain its code. In this demonstration, we have used LCD to display the data because Arduino has a built-in library for LCD. The data is given as input using VGPS as shown earlier, and here also we have given input two coordinates, and the coordinates are shown in the LCD screen, and we can see that the coordinates in the VGPS is displayed on the LCD screen. Here we can see the PCB layout and the 3D rendering of our model. And now moving on to the next presenter.
So now I'm going to demonstrate the screenshots of the photo gallery. In the photo gallery section, I'm going to show you the output. So as you can see that from the using the Arduino, we have interfaced the GPS module, and the GPS data and the LCD display is matching. For example, we have shown the EC building coordinate, and the coordinates displayed in the GPS module is being displayed in the LCD. Moving on. The same thing is shown in also using STM32 Cortex M4. Here we can see the map and the GPS coordinates being displayed in the virtual terminal and the GPS module also. Moving on. Some future outlooks we are going to implement is that the PCB layer that we have shown was not that much compact, so we are trying to do it much more compact by optimization. We can also add GSM module to make it an anti-theft device, and we want to make it much efficient so that it can access multiple data at the same time. And finally, we want to make sure that our GPS module is highly sensitive and has greater tracking abilities. Moving on. So there are some limitations for this project due to our COVID-19 pandemic and unavailability of components. We couldn't implement the hardware implementation. So it's in our mind that we might do the hardware implementation in future. And due to Proteus simulation issue, we couldn't interface GPS using Cortex M0 processor. So we had to do it in Cortex ARM Cortex M4 processor. Now, finally, we want to summarize this all. In this project, we have used GPS model and interfaced it with STM32 and Arduino Uno. We can use Wi-Fi model so that our GPS data can be secured in the server, and we can assure that by the further studying we can improve this system. Now, thank you for staying with us, and if you have any question, feel free to ask. Thank you.